How's everybody doing? All right. Can you guys hear me? Yeah, okay. Go to your emails, and you should have gotten a survey from me. Raise your hand with a little raise your hand symbol when you have gotten it and opened it up. Don't proceed through it because it's missing some things.
When did you send the email?
I sent it this morning, but it may not have arrived yet.
Yeah, I haven't gotten anything yet.
Okay, all right. It won't come from me, it will come from SurveyMonkey.
I also don't have one of those
Okay.
yet.
All right, then we'll proceed without it. It would have been better had it sent it out. But anyway, behind me on the board, can you guys see my board clearly? Okay. This is we're talking about Likert scales, and these are these scales where you know you might say you might be asked, for example, to rate this piece of awesome taxidermy. Yes, this is a piece of taxidermy that is in my office. It is a white possum. Stunning, isn't it? Amazing. And so you might be asked on a survey, for example, to what degree do you agree with the statement? That possum is beautiful. And you might say strongly disagree. You might say disagree. You might say neither agree nor disagree. You might agree, or you might strongly agree to the statement that is a beautiful possum. So raise your hands if you strongly disagree. Two people strongly disagree. Disagree. 4 people disagree. Neither agree nor disagree. You're neutral on it. Logan? Agree? I think this is everybody, right? Strongly agree. Okay. So what a Likert scale would do is it would assign a value of 1, 2, 3, 4, and 5 to these statements. And then what you would do to analyze these data mathematically is you would go, there are 2 1s, there are 4 2s, there is 1 3, and there are no 4s and 5s. And then they would take those data and they would say, okay, 2, 4, 6, 8, 11, 12, 13, the sum of those values divided by the number, 13 divided by 1, 2, 3, 4, 5, 6, 7, divided by 7 values, 13 divided by 7, 1, 7, 6, 0, 1 point, that would be 9, 8, 56, 7 goes into 40, how many times? 5, 35, cetera, a week ago. So we would basically say that the average then is 1.85. This is the average possum score. Sorry, Blaine, you missed out on voting on the possum.
Oh, sorry, my bad.
That is the cost of being late for class. You miss out on the possum vote. So the possum didn't do particularly well. It had an average score of 1.85 out of 5 because you clearly don't value quality taxidermy. So in this case, you were given a scale that had statements associated with it. And this is oftentimes how you see opinion surveys done. This is how your course evaluations are done. Was DTS 218, you know, a good class? Was your teacher excellent or not? And you agree or disagree with those statements. But another way of kind of assessing opinions is to present you with a sliding scale. And this was the intention of the survey that I sent out, and I was hoping that you would have it in hand by the time we started class, but evidently SurveyMonkey did not send it out. So with a slider, which you can do nowadays because we have better technology, you can just grab a little dot and you can place it on a continuous scale from, for example, least desirable to most desirable, with neutral being somewhere here in the middle. And so what I want you to do is I want you to create 8 sliding scales either on your iPad or on a piece of paper in your room or something. So 8 of them in a row, and just have a dot at one end, a dot at the other end, and a dot in the middle to create 8 of them in order. Raise your hand when you have that completed so that I can move on to the next stage. All right, Jonathan got his done. You guys mind if I eat a little yogurt while I wait for you guys to get finished? All right. I had to do some chicken maintenance this morning. My backyard chickens. It's too cold, their water's not flowing, so I had to go out and fix the water. Logan's done. Haley. Haley's eating breakfast also. We're just having a breakfast class today. Hayden, are you done? Okay. I didn't see a raised hand, so. Is everybody done? Oh, okay. I'm waiting for the raised hands to appear. All right, take your raised hands down. All right. I'm going to now show you 8 pictures rather. Let me share my screen. And these pictures are pictures of cars. And I want you to rate them on the basis of desirability on a scale from least desirable to most desirable. Give me just a minute to square myself away Zoom-wise here. So here they are. Let's see. Okay, so this is car number 1. So what I want you to do is just on the scale, put another dot, possibly in a different color if you want, of kind of where you place this car in terms of desirability from least desirable to most desirable. So this is, I think, a Mazda Miata or something like this. So, you know, just put a dot kind of wherever that is on the desirability scale for you for the first desirability scale. Hold on just a minute. Okay, so you guys have your mark for that one. All right, here's the second car. Mercedes station wagon. Everybody have your opinion recorded for that one? Everybody good? Hannah? Blaine? Okay. Third car. Ford cargo van. Give me a thumbs up when you're done. All right. This is a 1970s Yugo. It was a Soviet bloc car back in the 70s. Give me a thumbs up when you're done with that one. This is a Toyota Prius. Unfortunately, it's kind of a low resolution photo of a Prius. Thumbs up when you're done. All right. This is a Subaru Outback. Everybody done? This is a Chevy Impala. Everybody done? And this is a Lamborghini. All right, everybody complete. All right, below this scale, below those scales that you've just filled out, I want you to make another scale that spans the same distance, and I want you to go equidistant between the 2 endpoints and put a mark. And then I want you to put another mark equidistant between those 2 marks, so that you have 1, 2, 3, 4, 5 marks, 2 endpoints and a middle, and then midpoints between the middle and the endpoints. Let me know when you've done that with a thumbs up or something. Okay. make this endpoint 0, make this endpoint 100, make the midpoint 50, make this point 25, and this point 25. Now open up your chat function in Zoom.
Wait, I have a question. Wouldn't it be
Yep.
75 instead of 25?
Oh yeah, it would be 75. Yeah, because I'm losing my mind. 75. Okay. So open up your chat function. Let me see if I can get my chat function to come up. Chat. Oh, there it is. Okay. So in the chat, so now that you have that numerical scale, I want you to go back to the point that you put on for this first car, this Monza Miata, and I want you to estimate to your best ability what the numerical value would have been. So I put it right here. So that to me looks like, I don't know, around 62, something like that for me. And then report in the chat what your numerical value was. And I'm going to keep track of these. Car 1. 83, 85, 55, 60. 83, 85, 65. Wait, what did I say? 83, 85, 55, 55, 60. 55, 55, 60, 55, 55, 60. 80, 65, 65. 80, 65, 65. Okay. That was car 1. Can I clear chat? Is it possible to clear chat? Whoa. Okay. Oh, I just lost Zoom for a minute. Okay, I can't clear chat. So we're just going to continue. Now, so this was car 1, 2, 3, 4. This is car 4. Go down to car 4's ratings and do the same estimate, and then put your numerical estimates in. Zero, 0, 10. Man, you guys are really harsh on the whole. You go 25, 5. 5, 35, 27. 0, 0, 10. 25, 5, 5, 35, 27. Okay. All right. This was car 4, right? 1, 2, 3, 4, 5, 6, 7, 8. Now give me your ratings for car number 8. Okay, let's see. 100, 90, 100, 90, 100, 96, 75, and 95. Okay, so you're like, I know you guys are probably thinking, what the heck is he doing? Okay, so for the first one, car number 1, if this is 0, 25, 50, 75, and 100. For the first car, we have something up here around 83, 85, 55, 55, 60, 80, 65, 65. For the Yugo, which is one of the most despised cars in the history of cars, we have 0, 0, 10, 25, 5, 5, 35, 27. For the Lamborghini, we have 1, 2, 3 100s, 1, 2, 3 100s. We have a 96. We have a couple. We have a 96, a 95. We have a couple of 90s. We have 175. Okay. So when you look at, oh, I should have done those in different colors actually. So when you look at these distributions, one of the things that if we thought in a Likert scale sort of way, we would have seen clusters of points right around 50, right around 0, right around 25, right around 50, right around 75, and right around 100. And it looks like we have that, except that they're all on the upper side of 25, 50, 75. And then, of course, they have to be on the lower side of 100. But here's one of the things that I want you to notice. The Miata, which is kind of a sportier sort of car, I don't know, this was kind of billed as like a sporty coupe. And clearly you guys like sporty cars because there was resounding desirability of a Lamborghini, such that some of you had a much stronger response to a Lamborghini than you did to a Miata. And the range of scores for the Miata were much broader in terms of their variation than for the Lamborghini. What this indicates, and it's not surprising, I chose these different suites of cars for a reason. What this reveals, though, is that you have the distance between, so if this is least desirable, if we were to put verbal categories on a somewhat desirable, what do I want to say? So if we said least desirable, somewhat desirable, moderately desirable, substantially desirable, and extremely desirable, if I had given you these verbal statements in a Likert scale, to move you from a Mazda Miata, which falls somewhere between moderately desirable and substantially desirable, to get you to move there, I have to give you a Lamborghini to get you to shift out of this range into this range. I don't know what other cars would have shifted you out of a Mazda Miata range to a Lamborghini style of response. Give me some other cars. Unmute yourselves and give me some cars that you would put in the same category as a Lamborghini.
G-Wagon.
Well, what is that? I don't know what that is.
Mercedes G-Wagon.
Oh, okay, is that some sporty supercar Mercedes?
No, it's not like a sport car.
Oh, okay. What is it? Let me go find it. Let's see, Mercedes.
It's
GYA?
it's a G wagon.
Oh, a G-Wagon.
Yeah.
Oh, that's a sports utility thing. Oh, gotcha. Okay. What about the rest of you? What would have done it for you on the extremely desirable car front?
A Ferrari.
A Ferrari. What else?
I'm a big fan of Range Rovers, so that would have done it for me.
Okay. Rest of you?
Tesla.
Ah, Tesla. Okay. Yep. Wish they had a
Bugatti.
longer range. Yeah, go ahead.
Bugatti.
Bugatti. Okay. Yep.
There's a couple BMWs out there.
Okay.
Probably
For
a
me,
Dodge Challenger.
A Dodge Challenger. For me, the one that does it for me is a Toyota Prius. I own two of them, a 2007 and a 2019. The 2007 made it up the hill this morning, even in the ice. It is the most awesome car on the planet. So when you think about all those cars that you guys just listed, those are all really high-end cars. So once again, what that indicates to me is that the distance between these two categories, moderately desirable and substantially desirable, and extremely desirable, that's not actually probably a distance of 25 points on this sliding scale from 0 to 100. It's probably a much greater distance from moderately desirable or substantially desirable than either 50 points on the scale or 25 points on this scale. In the same way, the Yugo was down here in the basement, which once again indicates to me that this least desirable category is probably substantially further away from somewhat desirable than 25 points. So this scale probably is more likely scaled something like this. If we were going to give you, if I had given you verbal statements, you would have had to have chosen between either this or that or that or that or that. So they would occur at these breakpoints, but based on your responses in response to these cars, I would argue that these breakpoints are not equidistant apart. I think it takes a lot more for you to go to extremely desirable and a lot more for you to go to least desirable than it takes for you to distinguish between these things in the middle. Once again, just based on kind of how you clustered when you had a sliding scale. Notice how I didn't put numbers on the sliding scale when I first gave it to you. I just gave you the endpoints and what the endpoints meant and what the middle is. And then after you had placed your points, I asked you to then space that scale out equidistant and estimate what the numerical value would be. But if they were actually equidistant, what we should have seen was more continuous variation. I'm sorry, if they were actually equidistant, we should have seen clustering around 0, 25, 50, 75, and 100, but we shouldn't have seen a lot of big gaps in that. It should have been kind of continuous variation because you put things on a sliding scale. We would have seen, you know, more stuff kind of like this going on. But you had really strong responses to one car you had pretty strong responses to another car, and then you had some responses in the middle. And I would be interested in seeing what your numerical scores were for all of the cars. So for Wednesday, if you could send me in an email, car 1, car 2, car 3, car 4, car 5, car 6, and car 7, and then what your numerical values were, I'll prepare those for Saturday, or for Wednesday rather. But if we were going to take these things and say, well, least desirable is a 1, somewhat desirable is a 2, moderately desirable is a 3, substantially desirable is a 4, and extremely desirable is a 5, which is what we usually do when we use Likert scale data, which is what we were talking about last time in class. The distance between 1 and 2 is not the same as the distance between 2 and 3. That's not the same as the distance between 3 and 4. And the distance between 4 and 5 isn't actually 1 unit wide. When you are given the opportunity to respond to these things on a sliding scale. So when we go, can you guys still see my screen that I'm sharing? It has a big scary bug on it. So when we go to see, we were discussing these excerpts that I had given you last Wednesday, which now seems like an eternity ago. When you see these statements, like on the other hand, all qualitative information can be easily converted into quantitative, and there are many times when doing so would add considerable value to your research. The simplest way to do this is divide the qualitative information into units and number them. What we're basically saying is that we can take this verbal statement and convert it into a 1, this verbal statement, convert it into a 2, this verbal statement, convert it into a 3, this one, convert it into a 4, and this one, and convert it into a 5. Well, clearly, this statement represents a range of opinions. This statement represents a range of opinions. This statement represents a range of opinions if we're going to try and make this numerical equivalency. That range is borne out when you put things on a sliding scale, but when you give people categories to put these things into, it basically reduces their choices, their options, and they have to choose. And if you give them moderately versus substantially versus extremely, moving them from one category to the next category may require really big differences. And if it does require big differences to move you from responding substantially desirable to extremely desirable, then this scale is no longer equidistant, which means that the difference between 4 and 5 is actually, in reality, in people's minds, a much greater distance than the distance between 3 and 4. As soon as you have that problem, that the actual distance in people's minds between what gets numbered 4 and 5 is much greater than what gets numbered 3 and 4, you can no longer start averaging these things up, because this represents a larger difference of opinion than this represents. And so I would argue, and other people who do research in this area would also argue, is that simply dividing these responses, strongly disagree, disagree, neutral, agree, strongly agree, dividing these up and giving these things numbers, and each number is equidistant from one another, doesn't actually take this qualitative data and make it quantitative. I would argue that the quantitativeness of it, converting it to numbers, can actually obscure differences that would be revealed if you used something like a sliding scale, which is why oftentimes opinion polls rely upon a sliding scale rather than a set of Likert items. So when we go back to these different levels of these different scales of numbers, of data, nominal data, things like colors, ordinal data, things like verbal statements that can be ordered, but don't have numerical value, versus interval, where the intervals actually matter. If I say 1 and 2 and 2 and 3, the intervals between those things are the same. To ratio scale data, you can take ratio scale data and convert it into interval, convert that into ordinal, and even convert that into nominal if you wanted. I don't know why you would want to do that, but you can't take nominal data and convert it into into ordinal data. Blue versus red versus green, those are categories that don't have any sort of logical ranking system. You can't take colors and convert them into ordinal data where blue is greater than green, green is greater than yellow, yellow is greater than red. In the same way, you can't take ordinal data, things like strongly disagree, disagree, neutral, agree, and strongly agree. You can't take those things and convert them into interval level data unless you can be sure that strongly disagree and disagree are the same distance apart on the interval scale as disagree is from neutral. And those two differences are the same as the difference between neutral and agree and strongly agree. So you can take these verbal statements and convert them to interval scale data, but only if you can provide some evidence that these things are actually at set intervals. And I would argue for most opinion data that people gather in surveys, it's very difficult to make that case, especially when you give one group of people the Likert scale data like this, and you give another set of people the same survey, but give them a sliding scale. And what you see when you do that, typically in the research that's been done, is that the sliding scale data end up looking very different from the Likert scale data. And it's because these intervals between merely disagreeing with someone and strongly disagreeing with someone is generally going to be a much greater gulf than being neutral about something and disagreeing with a particular statement. Do you agree or disagree, or are you just kind of neutral? Well, that's kind of a wishy-washy middle ground. Do you disagree or do you strongly agree? To get to the strongly disagree part, you would probably have to have much stronger feelings about whatever that is. And that's the reason that you should probably avoid converting Likert scale data to numbers and then trying to analyze it with things like averages. It's much better to just look at these things as distributions and then use distributional tests to see if there are differences in terms of differences in responses to particular questions or differences in responses about different opinions about things. Questions about that? How do you feel about Likert data at this point then? You're surrounded by Likert data, by the way. It is everywhere. Opinions?
I have a question.
Yeah.
Are you saying Likert data?
Likert. It was invented by a guy named Likert. Likert. Sorry, I should have probably written that on the board. Likert scale data are these kinds of data where you have verbal statements describing this continuum of responses, and then you convert it. It was published back in 1932. It's a very old technique. Some people refer to his name as Likert, but that's not actually how he pronounced it. Not what I wanted to do. Can you guys still see my screen?
Yeah.
Likert, 1932, a technique for the measurement of attitudes. He was a proponent of doing exactly what I'm saying you should not do. And it's used commonly in sociological research and economic research. public opinion polls about everything from whether or not Biden should, have a 1.9 trillion COVID relief package, and whether there should be a $15 minimum wage portion of it, to whether Mitch McConnell looks like a turtle. These are all given in the form. Logan just chuckled to himself. These are all the kinds of surveys that would give you verbal responses and then assign numbers to those things, and then try and analyze them. But one of the things that you see nowadays in public opinion polls is that they don't actually report those values as averages anymore. They tell you what percentage of the people agreed versus disagreed and things like this, because people who do public opinion polls have come to the conclusion that adding those values up and saying, do you approve of the job that Biden is doing, or for that matter, did you approve of the job that So if you ever get called by a pollster and are asked, for example, do you approve of the job that Biden is doing, or back in the Trump administration, do you approve of the job that Trump is doing? You would be asked to strongly disapprove, be neutral, approve, or strongly approve. They don't then add all those things up, multiplied times whatever the values are, 1, 2, 3, 4, or 5, and then report those averages. When you look at approval rating data, what they basically say is, 45% of Americans, strongly or moderately disapprove, which means that 55% of Americans are in the neutral to strongly approve category. This is how they always report the data. So even public opinion pollsters who have actually taken kind of a rough beating the last 5 years or so have gotten away from handling these kind of data this way. And so you could, for example, go to 538. Whoa, that's not what I wanted to do. 538, which is it's a polling situation. It's a polling site. You could look at, the popularity of Biden. You could see, once again, what percentage of Americans approve versus disapprove. And what they've done is they've just aggregated the disapprove categories and the approve categories, and basically said, in response to different polls, where are people sitting on Biden's approval versus disapproval? And so they're not adding up. They're not taking the individual responses, multiplying times a 1, a 2, a 3, a 4, or a 5, and then reporting these things out as averages. They're actually reporting them as proportions, which is the appropriate thing to do with this type of data. So what are your thoughts about how to handle different kinds of data? You guys are opinionless. that what I'm to believe?
We're all neutral.
You're all neutral. That is not a good place to be where data are concerned. All right, well, think about it, because you do have to make decisions sometimes in terms of how you analyze data. And people will bring you data and you will disagree with them on how they should be handled at times. And those will be difficult conversations to have with people when they think that you should be analyzing their data a particular way and you want to analyze their data a different way. And sometimes it may take you weeks to convince them that your way of going about doing things is the correct and proper way of doing things. But as always, you should base your decision on how to analyze data on the best available evidence and statistical practice that you can have access to. And so it's important that you go and read literature about how to handle different data types. Don't just take my word for it. You should go out and inform yourself in the primary literature about how to handle different kinds of data. What I want us to do now is to start thinking about distributions more formally. So ultimately, what we want to be able to do with the data that you guys are handling in a data science context and be able to make decisions about what those data mean. And so I used to teach this class mainly for biology students who were planning on going to graduate school. And when it got shifted into a data science program class, I've shifted kind of what a lot of the examples are and kind of the way in which I approach the whole thing. So you guys are in data science. You guys, I think, are virtually all data science majors, except for I think one person might be an econ major. Chance, are you? No, okay, everybody's data science. So when you think of your role as a data scientist, how do you view that role? This will help give me some insight into where you're coming from.
I'm not a data science major, I'm a minor, but how I view my role is like using this as a tool for my future career to be able to like make decisions. That makes sense.
Okay, so data science for you isn't just about collecting and organizing the data, it's also about doing something with those data and making decisions about those data. Am I understanding that correctly? Okay, all right, good. Well, what about the rest of you?
Well, when I hear data science, I consider more gathering the information and figuring out how to gather this information, and then basically creating tables, graph, anything that's necessary for you to present the information is what I hear when I think of data science, or is what I think of when I hear data science.
Okay, so you're more about, you think data science is more about wrangling the data, organizing the data, and visualizing the data. Okay.
Yeah.
Okay.
For me, it's like the second half of that. It's more like organizing data to create something that's understandable for everybody else.
Okay.
Like creating graphs that people would understand.
This explains some of your responses after live coding. I've gotten strong responses in your responses after live coding. Like you guys really like graphing data. That's been a recurring set of comments. Who else?
I mean, I would use it to answer a question. So I would go, I have a question that's scientific based, and then use it to use mass data to answer that question, and then put it in graph so someone else can understand it as well.
Okay. Yeah, certainly having an answer that is provided by the data that you have doesn't really gain you much if you can't communicate that effectively to other people. So certainly visualization is always going to be part of this. What about the rest of you? How are you viewing your role in data science?
I'd say I view it as like kind of similar to Haley, as far as like analyzing the data and making it useful for other people.
Okay. Hannah, Logan?
I was gonna say the same thing, just kind of like The way I'm like thinking of the way that I want to use it in the future is like helping find the best result with the data that we're given.
Logan, you were about to say something?
Yeah, basically, I agree with like Haley and Sam, just to like visualize the data and see it in graphs.
Right. Well, visualizations are fine, but they don't necessarily help you make decisions about data. I generally take the approach of finding the answer in terms of decision making about data. And then the trick after I found that answer is then how to best visualize that answer so that an audience will understand it. So we're going to be doing both, but this class really is about decision making about data. So decision making comes first, and then visualizing what that decision looks like comes after that. And so everything we do, there will be an analysis component, then there will be a visualization component. But for me, doing one without the other doesn't really make a lot of sense in many cases. So back to making decisions about data. The way we make decisions about data is often based on the central limit theorem, this idea that there's a population of observations out there, and we want to know something about that population of observations, but we can't possibly sample that entire population completely. So we rely on sampling from that population. That sampling gives us a sample mean, and then hopefully that sample mean tells us something about the population, and the amount of variation around that sample mean tells us something about the amount of variation that is in the population that we drew that sample mean from. So when we did the card drawing exercise, which I started looking at those over the weekend, we saw that when we only drew 2 cards out, the distribution of sample means was quite wide. So drawing only 2 cards out of a deck of cards doesn't really tell you a lot about the deck of cards. Drawing 5 cards out of the deck of cards tells you more about the deck of cards than drawing 2, but doesn't tell you as much as drawing 10 cards. And if you draw 20 cards, it tells you even more. And if you draw 30 cards, it tells you even more, because you're sampling a larger and larger proportion of the population that you're interested in knowing something about. And as you see, even with only 2 cards, the average of the distribution of sample means is clustered right around what you expect the average to be, right around 7. But the amount of variation around that population mean is quite wide. But by the time you get up to 30 cards, when you draw 30 cards, each sample mean doesn't really vary much from other sample means, which is why this distribution is much more narrow. And so this is why when you go and gather data, you want to have a sample size that is sufficient to give you a narrow range of variation around that sample mean, so that if you draw a sample mean from one population and you draw a sample mean from another population, you can tell whether or not those 2 sample means are different from one another. And so we're almost always going to want to be looking at sample means and seeing if one sample mean differs from another sample mean. And so we might sample a population of individuals by age group, for example. So we might sample people from 18 to 25 and people from 25 to 35, 35 to 45, et cetera, and basically, ask them what's the put a numerical probability on their probability of getting the COVID vaccine, for example. And then we could look at those responses, which are numerical responses. It's people estimating the probability that they're going to get a vaccine. And we could average those up and see if the averages differed between young people, middle-aged people, old people, et cetera. Have any of you guys been vaccinated yet? No, we're not going to be vaccinated for a while. I just filled out my Clay County Health interest form for being interested in a vaccine, because when it's available and I'm able to get it, I have a 100% chance of going and getting it. So we want to know, are there differences among these different age groups in terms of their likelihood of going and getting vaccinated? That's a useful piece of information to know. But in order for us to know that, we need to sample the population. We need to get the responses from the population. We have to know what the average of that sample is, but we also need to know how much dispersion around that estimate is so that we could tell whether 18 to 25s are more or less likely to get the vaccine than people who are in their 40s or 50s. And so we have to know not only the point estimate of the average, but we also have to know how much variation there is. And the larger sample we take, the less variation there is. So what I want to start going through with you today is the procedures by which we build confidence intervals around our sample mean estimates so that we kind of know what the level of dispersion is. Some of these calculations are going to be familiar to you. Other of these calculations are not. So I think the next slide here is a blank slide. So some students have mentioned that it's hard to see things on the board. So I'm going to try a different technique today. So let me get that queued up. You can't see my screen anymore, right? Correct? Okay, all right, good. Whoa. Can you now see my iPad? Okay, cool, awesome. Yeah, I've already done that. Thank you. See a blank screen? All right, cool. All right, let's do this then. So anytime you have a sample of interval or ratio scale data, you can do all kinds of mathematical operations on them. So you can look at their distributions, of course, but you can also do things like calculate means and compare means. So whenever I use the term mean, the mean, can you see the writing on the board? Yeah, okay. The mean is symbolized by an X with a bar over it. So anytime you see something with a bar over it, that basically signifies some sort of average value. And when we calculate the mean, we just add up all of the X values and we divide by the number of values that we have. So let's just make up a simple data set where the X values are 1, 2, 3, 4, and 5. 5 and 4 is 9, 9 and 3 is 12, 13, 14, 15. So the sum of the X values in this case is 15, and the number of values that we have is 5. And when we divide those, the average then is an average of 3. So that tells us kind of where the middle of the data set is in this case. But what's important for telling whether a mean of 3 is different from, for example, a mean of 5 is not just whether the numbers are different, is 5 different from 3, but also how much variation there is around that estimate of the mean of 3 and that estimate of the mean of 5. So, so that's the mean of 3. Well, in order to get to a way that we can make decisions about whether a mean of 3 is different from a mean of 5, that requires that we ultimately look at a thing called a 95% confidence interval. But to get to what a 95% confidence interval is requires a series of intermediate steps. The first step that we have to do is we have to calculate the sample variance. Now, the sample variance is usually indicated by the abbreviation S raised to the square. So S squared is sample variance. But the way we calculate sample variance is by basically taking each X value, subtracting the mean from it, squaring that, adding all of those up, and then dividing by the degrees of freedom, which is 1 minus the sample size. So this type of notation is oftentimes going to be confusing to students, but it's really pretty easy. The sigma symbol in front of anything means that you're adding things up. So this is a summation symbol. Summation. And this is simply x sub I is the different x values, x1, x2, x3, x4, and x5. The mean is the mean, in this case 3. These two things are squared, and then they're divided by whatever n minus 1 is. N is the number of values that you have. So this would be 4 in this case. So it's 1 minus the mean squared plus 2 minus the mean squared plus 3 minus the mean squared plus 4 minus the mean squared plus 5 minus the mean squared. So what we would do to calculate the variance is we would subtract the mean from each of these. And what that gives us ultimately is, it gives us a minus 2 here, a minus 1 here, a 0 here, a plus 1 here, and a plus 2 here. But notice that if we sum those all up, the sum adds to 0. Well, that makes sense because the mean is right in the middle of the data set. And so there are going to be just as many values and of equal weight to one side of the mean as there are to the other side of the mean. And this is the reason why we take those deviations from the mean and we square them. Because then that converts everything to positive values, positive value of 4, positive value of 1, 0, 1, and 4. So down here, where we square the deviations of the individual data points from the mean, the reason we're squaring is so that this thing doesn't sum to 0. And so that sums to 10. And we would divide that then by 4. And when we divide 10 by 4, that is 2.5. So in this case, the mean is a mean of 3, and the variance is 2.5. Okay? The only reason we are calculating the variance is because that gets us to the standard deviation. The standard deviation gets us to the standard error, and the standard error gets us to the confidence interval, the 95% confidence interval. But what I want to do before we move on from that is I want to talk a little bit more about the variance. This thing here, this operation right here, where you take an individual data point, you subtract the mean from it, and you square it, and then you sum those things up across all of the data that you have. This is referred to as the sum of squares. In statistics books, you will see it shorthanded SS. If you take out your textbook, which we're going to start relying more and more heavily on, and you turn to chapter 7, which is the first set of analyses we're going to be doing after we, no, not chapter 7, chapter 8, on page Well, on page 174, if you look on page 174, there is a ANOVA table for some species diversity data. And there's an ANOVA table there in the middle of the page, and you'll see that the second column, the first column says source, the second column says SS. That SS is the sums of squares. And so this is an idea that you are going to be confronted with over and over and over again in this class. So it's important that you recognize what the sums of squares is. Another way of saying it is the sum of the squared deviations from the mean. So if the mean is 3, we have back up. We have one value that is at 1, one value that is at 2, one value that is at 3, one value is at 4, one value is at 5. The deviation from the mean of 3 is 0. The deviation from here is -1. The deviation from here is -2. That gets squared. That gets squared. The deviation here is 1. The deviation here is 2. That gets squared, and that gets squared. So the sums of squares are the sum of the squared deviations from the mean. And like I said, we're going to be seeing that a lot. Oftentimes you also see in statistics books, this is referred to as the residual value. So this shows you residual variation that occurs around the mean. And I see that we are at 8:53, so we've run over a little bit. So we'll continue this conversation on Wednesday, working towards the confidence interval and how you calculate confidence intervals. Questions?
Do you want us in class Wednesday or on Zoom again?
No, Zoom again on Wednesday. We'll probably be back in class again, maybe on Friday, depending on how quickly we get through things on Wednesday. All right. All right, then. I'll see you then.